All right, so let's get started. We're going to kind of pick up where we left off last time. We were talking about the energetics of our solution formation here. And we left off with this question of like why oil and water don't mix. Remember, in order to create a solution, what has to happen from an energetic standpoint is we got to break up the interactions between neighboring solute molecules. That requires an input or an increase of energy. We got to break the interaction between neighboring solvent molecules. And then when they mix them together, we form these new interactions. Well, oil only has these weak dispersion forces, so we only got to put in a little bit of energy to break that. Water's got these really strong hydrogen bonding interactions. We got to put in a lot of energy to break that. But then oil and water can only dispersion, interact with one another, so the release of energy that we get is very small. And so that process requires this net input of energy, and that's bad, all right? So first of all, let's just kind of compare and contrast a favorable versus an unfavorable solution formation. So we're going to say energetics of solution formation. Okay. And we're going to compare something that's unfavorable and something that's favorable. All right, we're going to make our little graph again. So we're going to look at unfavorable first. Okay, our little graph is going to have this increase in energy. So energy's on our y-axis here. And we're going to start down here on the bottom. So this is our initial energy when we have our solute and our solvent separate from one another. All right, let's even just say solute and solvent are separate. All right, well, we always have to put energy in order to break these intermolecular forces. So the first thing we're going to do is we're going to put energy in to break, I'm going to abbreviate IMF in our solute. So now we've raised our energy level to here. As we put energy in, we got to put in even more energy to break our intermolecular forces in our solvent. All right, so this one will sort of do like oil and water, where we have to put a lot in to break those forces in our solvent. Okay, so now we're all the way up here. We've increased our energy quite a bit. But then when we mix these two things together, we get this release of energy. All right, and as in the case of oil and water, if we only get a release of a little bit of energy, all right, so we'll say we release energy as these new IMFs form. Let me clean this up. Handwriting was terrible. All right, now we're here in terms of our energy. So if we look at where we started and where we finished with our solution, we see we required this net input of energy. We had to put so much energy in to break the interactions between neighboring solvent molecules and neighboring solute molecules, and then we only got a little bit out when these things mixed together, right? So there was a net input of energy that happened when we created this solution, all right? This net input of energy, we have a fancy term. We call this an endothermic process. Okay, so net input of energy, endothermic. And generally speaking, endothermic processes are not very favorable. There are a few exceptions, and we'll talk a little bit more about this when we get to our thermodynamics chapter, but by and large, the universe really likes things that end up in a net release of energy. So things that require an input of energy are not very favorable from the universe's standpoint. From the simple example of oil and water, water would much rather interact with neighboring water molecules through those strong hydrogen bonding interactions than make room for those oil molecules and only be able to weakly interact with them through dispersion forces. All right? So this would be an example of an unfavorable solution formation, and by that we simply mean it's not going to happen. You're going to mix these two things together, and rather than form that homogeneous mixture, that solution, they're going to form those two layers, like we would expect when we mix oil and water together. All right, on the flip side, we're going to do our favorable solution formation here. All right, and we're going to kind of start in the same place. Now we're going to put energy in to break our interactions between our neighboring solute molecules. Again, that necessarily takes us up in energy. Okay, we're going to put even more energy in to break our interactions between our neighboring solvent molecules. So again, now we're at a higher energy level. But now we're going to mix these things together, and if they form really favorable interactions, if our solute and solvent form very favorable interactions, that means we have a large release in energy. All right, so we release energy as these new IMFs form. And now we're all the way down here. This is where we finish with our solution. Did this require a net input of energy? Yep. We had to put in energy, but what about a net input of energy? No, right? I ended up getting more energy out than I had to put in. Right? So if I just look at the simple difference between where I started and where I finish, okay, this is a net, I gotta make some room here. Let's do this. Take it all the way over here. This is a net output of energy, or what we call an exothermic mixing. All right, so these little charts here, what we're trying to illustrate, first of all, is this unavoidable fact that we have to put in energy first to break interactions in our solute and our solvent, and we'll always get a release of energy when new interactions form. That's just a basis of chemistry. To break stuff, you got to put energy in. When new stuff forms, you get energy back out, all right? But the question is, what's the balance between those two? How much energy do I put in? How much energy do I get back out? If this mixing is exothermic, that's going to be a favorable process. If it's very endothermic, it's not going to be a favorable process, meaning that they're not going to mix, all right? So what we're going to say here is, in conclusion, all right, a solution will form if our mixing is either exothermic or there are some exceptions, and again, we'll talk about why the universe will allow these weird endothermic processes to occur, but they can only be slightly endothermic. right? But the bottom line is the amount of energy that we put in, we should get a similar, if not more, amount of energy back out when these things mix together. That's a favorable solution formation. Okay, so there's this phrase that you'll hear in chemistry, like dissolves like. All right, and what do we mean by that? That's a shorthand for polar solvents will dissolve polar solutes and nonpolar solvents will dissolve nonpolar solutes. All right, but polar solutes will not dissolve in nonpolar solvents, and nonpolar solutes will not dissolve in polar solvents. Did I say the same thing twice? Okay, polar solutes will not dissolve in nonpolar solvents, and nonpolar solutes will not dissolve in polar solvents. You can't mix and match them, right? You got to be both polar or both nonpolar. That's because if I'm going to put in a lot of energy to break interactions in polar solutes and a lot of energy to break interactions in polar solvents, I want a big release of energy when those two interact with one another. Likewise, even if it's nonpolar, and I'm just going to put a little bit of energy in to break my dispersion forces in my nonpolar solutes, and a little bit of energy to put in to break my dispersion forces in my nonpolar solvents, I need an equal amount of energy that's released. And they're not going to form like hydrogen bonds with one another, right? They're going to form those dispersion forces again. Okay? So we have this simple phrase, like dissolve like. Polar solvents dissolve nonpolar solutes, and nonpolar solvents dissolve polar solutes, dissolve nonpolar solutes. Okay, so on this topic of dissolving stuff, solubility, we're going to sort of now focus specifically on ionic compounds and how they dissolve in aqueous solutions. Okay, so this concept here works for, when we're talking about intermolecular forces, that works for just molecules more broadly. We're going to kind of now dive in and do a deep dive specifically on the solubility of salts or ionic compounds and how they dissolve in water, right? Remember, those will form those really strong ion-dipole interactions. Okay, so this is this concept of solubility. All right, we're going to talk about the amount. Solubility is going to be like a numerical value. We're going to be doing some math here. We're specifically going to be talking about the amount of solute, the maximum amount, let's say, of a solute that will dissolve in a solvent. All right, so I'm going to introduce you to our constants page for this chapter here. On our constants page, the first thing that we're going to take a look at is this graph here. Okay, so this graph here has a number of different ionic compounds on there. We got sodium nitrate, calcium chloride, lead 2 nitrate, sodium chloride, potassium nitrate, potassium chloride, potassium permanganate here, or not permanganate, I'm sorry, dichromate, etc., etc. All right, we have these different ionic compounds, and what we have is their solubility as a function of temperature. Okay, so like I said, on your constants page, anything that appears on your constants page, you can expect to see on your exam. This isn't a chart anybody has to have memorized or anything like that. But what we're going to do is we're going to learn how to use this as a tool. Okay, so I'm going to just copy this over. Into our notes here. Whoops. in our discussion of solubility. And as we said in our definition, this chart is telling us the maximum amount of a particular solute, in this case a particular salt, that will dissolve in a particular solvent, which is in this case water. All right? What we want to do is look very closely at this y-axis here. This is telling us our solubility in grams of solute per 100 grams of water. All right? And as we can see on the x-axis again, it's as a function of temperature here. So let's just pick one salt and one temperature and make sure we understand what this chart is saying here. All right? Let's look at sodium nitrate at 10 degrees Celsius. All right? So sodium nitrate is going to be this orange curve here at 10 degrees Celsius. I'm specifically looking at this point right here. Cool? All right, so what this is saying is we got 80. So what is this telling me? All right, this is telling me that 80 grams of sodium nitrate, NaNO3, will dissolve in 100 grams of water at 10 degrees Celsius. All right, again, my solubility values here. Grams of solute, so this is 80 grams of solute, will dissolve in 100 grams of water. All right? So, if I had 40 grams of sodium nitrate, would that dissolve in 100 grams of water? Yeah, why? Because our solubility is what? The maximum amount. So I can get up to 80 grams of sodium nitrate in those 100 grams of water. Anything less than that will also dissolve. But could I get 100 grams of sodium nitrate to dissolve in 100 grams of water? No, I'd be left with 20 grams floating around, right? So that's what our solubility is. This is the maximum amount, all right? So let's just note, maximum amount of that sodium nitrate that will dissolve in 100 grams of water. That's what this chart is telling me here. Okay? So I want everybody to take a second, and you're going to tell me the maximum amount. All right, what is, so most basic thing that I could ask you about this chart is, what is the max amount of potassium chloride that will dissolve in 100 grams of water? I'm going to give you a specific temperature here at 50 degrees Celsius.
It's like 42.
All right, so first of all, we got to find our particular salt on this chart here. Right, that corresponds to this one right here, which would be this blue line. I'm going to have to find my specific temperature. I'm going to follow that up to where it intersects with that line right here. So following that over, whoops. Right? Yeah, so 42 grams. Now, somebody else might have looked at this and said, well, I think that's 43. And somebody else might have looked at it and said, well, I think it's 41. Okay? If you remember back to when we were doing measurements in Chem 1A, we don't have a very fine measurement tool over here on our y-axis because it's grouped by tens. Right? That's how our spacing is. So I know for a fact that it's between 40 and 50. That I'm certain about. All right? But we always have one estimated uncertain digit as well. So we have to have one estimated uncertain digit. In this case, because my known spacing is in the tens, our estimated digit would be in that ones place. Okay? So absolutely we could say, and again, if you're off by plus or minus 1, that's okay. But we're going to say 42 grams of calcium chloride. All right? And we're going to get in the habit of using this in this conversion factor type form where we say 42 grams of potassium chloride per 100 grams of water. All right, where we're going is we're going to end up using this in some math here. okay? Cool. And let's just make a note here. I want you all to make a note specifically about how we read this chart. As I just said, this should be read with, let's say, your last digit in the ones place. If somebody were to say, well, I think it's 42.3, they'd be just totally BSing that 0.3, right? That is just a completely made up number. I'm not even sure it's 42, because again, it could be 41, could be 43. Our uncertain digit is in that ones place. So when you read this chart here, you should be reading it with that last digit in the ones place. I was a little bit sneaky, and I don't know who caught it, but when I did my 80, I put a decimal point at the end right here to indicate that I was sure that that was a 0, right? That was my estimated digit, okay? Remember our sig figs here. We're gonna have some sig fig practice here today as well, okay? Okay, cool. So now we say we have 42 grams of potassium chloride that will dissolve in 100 grams of water, and this value is only good for 50 degrees Celsius, right? It changes as a function of temperature. So if I wanted to increase the temperature, I'd have to go to my graph and pull a new value out. All right? So now let's take this just kind of as a reference. Or we can just leave it here. And I'm going to ask, what is the max amount of our, we'll keep the salt the same, potassium chloride that will dissolve in 200 grams of water at 50 degrees.
We'll use that fraction of the conversion method.
So if 42 grams dissolves in 100 grams of water, how much do we think would dissolve in 200 grams of water? Double it, right? Okay, but we want to be able to, we can kind of do that math in our head. That one's pretty easy, right? I just doubled the amount of water, we double it. But what if I said 16.9 grams of water? All right, we want to be able to do that. And yes, we're going to use this right here as a conversion factor, playing the same game that you played over and over and over again in general chemistry, where you line everything up in such a way that your units cancel out beautifully and you're left with the units that you want. Okay, so let's change this to an ugly amount. All right, let's say we're going to go to 17 grams of water. We'll keep it at 50 degrees so we can use our same solubility factor here. But I want everybody to take a second and see if you can't calculate how many grams of potassium chloride we would have dissolve maximum in that 17 grams of water. So when we have our conversion factors, it's always like, do we multiply, do we divide? What are we going to do here, right? And it's all about the units. Whenever we do our math, what you really don't want to do, especially when you're taking notes, like maybe when you're doing quick scratch work on your homework or something, maybe you can get away with it. But especially when you're in class taking notes, be really good about putting your units down on your page. Otherwise, a week from now, you're going to flip back and you're going to see a page full of numbers and be like, all right, great, that means absolutely nothing to me, right? So be really good about putting in your units when we're doing our practice problems here. All right, so I'm going to start with my 17 grams of water. Again, I'm going to use my solubility like a conversion factor here. And I need to cancel out grams of water. I'm trying to be left in an amount or grams of KCl. So I'm going to take this and multiply it by that 42 grams of KCl over 100 grams of H2O. And I know that this is set up correctly because my units of grams of water cancel out nicely. Okay? So we're going to punch this into our calculator here. My calculator spits out 7.14, and my units are grams of KCl. Okay? But now we got to worry about sig figs. And I'm going to be honest with y'all. We're going to start this course with some fairly simple calculations regarding like solubility. We'll talk about molarity, stuff that I think might be a little bit familiar. We're going to kind of quickly graduate to some more complicated functions. And when that happens, we're going to quietly ignore sig figs and just kind of put that to the side. But for right now, for our very simple calculations, for a simple multiplication, division, subtraction, all that jazz, we're going to have to keep track of our sig figs correctly. Okay? So let's just remind ourselves here. 17 has 2 sig figs in it. I will note for these conversion factors here, the way that this works is that all the uncertainty is put in that numerator value. The denominator of 100 is considered to be exact. Okay, so all the uncertainty in that chart is in your grams of solute part. So meaning the 42 has all the uncertainty, my 2 sig figs. My 100 I get to treat as being exact, meaning I don't have to worry about it when I'm doing my sig fig calculations, or my consideration. So 2 sig figs and 2 sig figs, that's pretty easy. My answer should have 2 sig figs. So I'm going to do 7.1 grams of KCl, put a box around it, that's my final answer there. Okay? Cool, all right. Let me see if I can just grab this chart again so we can have it on the screen. And I'm going to make y'all do one from the ground up here. That didn't work too well. And I'm going to put a little bit of a twist on it here. All right, how many grams of water are required to dissolve, let's do 76.3 grams of potassium chlorate at 50 degrees Celsius. Okay, so step one, you got to read your chart. You got to get to that chart and pull that conversion factor, that solubility factor off of there. And then you're going to have to do some math, paying special attention to your units to make sure that you can tell me how many grams of water are required. All right, so I'm going to give you all a few minutes to take care of that one. All right, chat it up with your partner if you're stuck at all. Make sure you all got the same answer.
factor for the water.
We were finding it like
It's basically the same thing.
Okay, so let's read this chart here. Potassium chlorate. Boom, that's going to be my green curve here. I'm looking specifically at 50 degrees, so follow that up to that green line. I'm looking at this point right here. All right, so what do we think? 18, 19, 17, somewhere in there, okay? We got a little bit of wiggle room on that. That last digit is not certain. It's an uncertain digit. So any one of those would have been perfectly fine, okay? So I'm going to say it's 18. So I'm going to say it's 18 for the sake of my calculation here, grams potassium chlorate per 100 grams of water, right? This is what I grab from that data point on my chart. That's how I build it. Grams potassium chlorate per 100 grams of water. So now, I'm going to do my math. I'm going to start with my 76.3 grams. And what's given is my grams of potassium chlorate. I want to know how much water I need to dissolve that specific amount of salt. Okay, so I'm going to take my solubility here. Am I going to use it as is, or am I going to have to flip it upside down? Right, I'm going to have to divide by that solubility, aka flip that upside down, so that now my 18 grams of potassium chlorate are on the bottom, and my 100 grams of water are on the top. Okay, I'm going to punch that into my calculator. I get 423.8888. My units work out nicely. I can see that grams of potassium chlorate cancel out. I'm left with grams of water, which is what I want. And then how many significant figures should be in my answer? 2, because of my solubility chart. It only gives me a digit in that ones place, right? This is an uncertain measurement right here. So this is my, yes, I start out with a value with 3 sig figs, but my chart gives me 2 sig figs, because remember that 100 is exact, and my answer can't be more precise than my inputs, right? I got to choose whatever the fewer number of sig figs are, so I'm going to round to that position right there. Okay, now one thing that you want to make sure of when you're rounding sig figs, all right, 40, does the 3 round up or down?
Yeah.
So I keep it the same, right? So this is going to be a big mistake that people make is they say 42 grams of water, okay? This is a very simple mistake to make, to just chop off that 0 because it's uncertain or because it's not significant. If I told you I was going to give you $423.8, but I was just going to round it to 2 sig figs, and I gave you $40, you'd be like, what the heck? Where's my other $300 and whatever dollars, right? Remember not to change the numbers. So that 4's got to be in the hundreds place, the 2's got to be in the tens place, and I just need that 0 on the end. I don't have a decimal point in there, so that's not a significant digit. All right, so my final answer here, I would need 420 grams of water in order to dissolve that much salt there. Okay? What's up?
Would it be incorrect if we did like scientific notation for that?
No, not at all. 4.2 times 10 to the 2, it's perfectly fine. Yep.
How do you know when to put the numbers on the bottom on the side?
How did I know to flip this upside down?
Because I switched the 18 and the 76.
Oh, because this is what we've got from our chart here, right? This chart read 18 grams per 100 grams of water. So this, from this chart here, is where you build your conversion factor, all right? 18 grams per those 100 grams of water. The 76 is what I just started out with. There's no other units, nothing else associated with that. That one's all by itself. Yeah, so from this chart here, you will always pull out some number that's per 100 grams of water. That's how that chart works. What's up?
I was just gonna ask, like, if this is on an exam where a question comes up like this, the chart will be exactly the same.
The chart will be the same,
okay,
correct. Yep.
perfect.
Yeah, so anything on that constants page, you can expect to see exactly that on your exam. Yep, exactly that on your homework. This is the tool we're learning how to use here. Cool. All right. So there's one other fun thing that we can learn how to do with this chart here. Okay, and these fall under this umbrella of what we call recrystallization.
Oh, Professor, real quick.
What's up?
If we do take a test and they ask us about a polyatomic ion, will it be written out in the chemical form or will it be in the words and we have to just know the polyatomic ions?
At this stage, I am not quizzing you on your polyatomic ion naming or whatever. That's a Chem 1A thing. I'm punting that to the first semester, and that's not my job anymore. Okay?
Thank God.
Okay, you will hear me say them. I do want you to be comfortable with them and everything like that, but there was a time and a place for that, and there's no way I'm going to spend time going over all that. Okay? Okay, so recrystallization. This is this type of problem that we're going to learn how to do using this solubility chart here. So what is this all about? All right, so this is a purification technique. You will be introduced to this in your organic chemistry lab. It's a really easy, really popular way to purify a solid. All right? So let's say that we do a reaction. You know, we mix two reactants together and we get this solid product. Well, that solid product's necessarily going to be contaminated. Maybe by leftover reactant and product, maybe by some side, or rather leftover reactants, maybe by some side product from that chemical reaction. And I want to purify that product so I have it in its nice pure form. Okay? So purifications, there's 1,000 purification techniques that you're going to learn. This is one of them here, this recrystallization technique. All right? So how does this work? Step one, we're going to dissolve our solid in a minimal amount of hot solvent.
We're assuming solid a ionic solid too, right?
We're specifically talking about, it works for a lot of different things. We're specifically using this chart here, so we're still talking about ionic solids. Yep. Okay. So then we're going to cool that solution down. All right, why? What's going to happen? Okay, let's go back to our chart real quick. We noted that these were solubilities as a function of temperature here, right? My x-axis as I was increasing was increasing temperature. If we looked at the vast majority of these salts here, what happens to its solubility as we crank up the temperature? Solubility goes up. All right, there's one freaking oddball here, cesium sulfate, whatever's going on there, I don't even know. All right, but the vast majority of compounds, their solubility will increase as the temperature of that solvent increases. So let's say that I was using potassium dichromate here. I'm going to crank up the temperature so that I can dissolve my solid in there. It's got this high solubility. What's going to happen when I cool it back down? What happens to the solubility? It decreases. And remember, the solubility is the maximum amount of solid that I can get to dissolve. So let's say that I crank this up to 90 degrees and I had my 100 grams of water, I got 68 grams of my potassium dichromate dissolved in that water at 90 degrees. Well, then if I cool it back down to 10 degrees, now its solubility is only around 17, 18. What's going to happen to the rest of it? It's going to precipitate back out, right? What you're going to have is you're going to have this nice, clear, colorless solution, and then you cool it back down, and all these crystals start to form. All this precipitate starts to form because the solubility of that solid has decreased. And it turns out that that stuff that crystallizes back out is more pure than what you started with. All the impurities are left floating around in the water, all right? So what happens is when we cool it back down, we precipitate our pure solid out of solution. Okay, we're going to note it's more pure because those impurities are left in that solution. Now, I will say, this technique doesn't work if you have like some massively impure solid. The logic behind it is that your impurities make up only a small percent of what your solid was to begin with, right? So they're still left floating around, and what you get back out is more pure. Now, did you get everything out that you put in there? Right? Let's use this analogy again. I started with 68 grams. I cooled it down. I still have about 18 grams left in that solution. You always lose a little bit when you do your recrystallization, but the point being, you're willing to take that loss because what you got is that much more pure. All right, so again, a purification technique, and what we want to do is we want to do some math here. We want to figure out how much we actually get back out at the end of the day. What's our yield going to be of this recrystallization? All right, and this is just the same game of using this solubility chart, but using it at different temperatures and kind of combining that together. All right? Cool. Whoops. Let's get our chart. Okay, I want to purify let's pick one here. I want to purify 75 grams of this lead 2 nitrate. That's our goal here. Okay, so step one, we want to, as we said, we want to dissolve that in a minimal amount of hot solvent. We don't want to use too much. Obviously, we could just put 200 liters of hot water in there and it would all dissolve. But the point being is we're trying to get stuff to precipitate back out. So we're going to use the minimal amount of hot water that we can in order to get the maximal yield that we can. All right? So the question that I could ask you first is, what is that minimal amount of water? To dissolve, looking at my chart here, we'll go ahead and use a nice round number. We'll say we'll take it to 60 degrees. All right, so let's check out at 60 degrees. Here's my lead nitrate, this yellow curve here. So if I follow this up, right there, okay, I'm gonna say this is pretty much smack dab in the middle. at 95 grams of my lead nitrate per 100 grams of water, right? So from my chart, what I get is 95 grams of lead to nitrate per 100 grams of H2O. All right, and we're going to change the temperature. So I am specifically going to note here that this is at 60 degrees. All right, so now we got to do our math here. Okay, let's take our 75 grams lead to nitrate. I got my conversion factor here. Do I use it as is or flip it upside down?
Flip it.
I gotta flip it. Let's put grams of potassium nitrate on the bottom. Not potassium, sorry, lead nitrate. 100 grams of water. Punch that into my calculator, 78.947. Grams of H2O. All right. How many significant figures should I have in that number? 2. Now, this is where we got to be really careful. I'm going to take this number, and maybe you didn't see this coming, but I'm going to take this number and I'm going to do some more math with it. So I'm going to mark that bar there, indicating that I have 2 sig figs. But I don't want to go and round it right now. Because if I take a rounded number and then go and do more calculations with it, I can incur what's called a rounding error, right? Where my answer at the end is going to be different. Rounding errors are really annoying because sometimes you get away with it. Sometimes you round in the middle of a problem and it's the exact same answer at the other end and you're like, oh yeah, that wasn't a problem. And other times it does change the answer. So we're always going to be good. We're always going to round at the very last step, but we're going to keep this little bar here so that we know how many sig figs that number actually has. All right? A good rule of thumb, I mean, my calculator spit out, what is that? 8 extra digits beyond the decimal place. If you keep 2 or 3 beyond your sig fig, you'll be just fine. Okay? All right, so now, again, step 2 is we have to cool this solution down. All right, we got that 75 grams of that lead nitrate dissolved in that minimal amount of water. But now we're going to cool that solution back down. All right, so we're going to cool this solution to 0. We're going to throw it on ice, 0 degrees Celsius. All right, let's first grab that solubility. All right, so let me just go back to our table here. We're again looking at our potassium nitrate, so now I'm going to follow this line all the way back down to 0 degrees Celsius. All right, between 30 and 40, I'm going to say it's 37, 36, somewhere in there, right? So this is going to be now our new solubility factor, 37 grams of lead nitrate per 100 grams of water. And let's just note this is our new one at 0 degrees. There's 2 things that I could ask you about this recrystallization problem here. The one, which is generally speaking what you care about the most, is how much pure product did we get? All right? But before we can answer that, we're going to have to figure out how much of that lead nitrate is still stuck in our solution. Right? Because not all of it precipitates back out. I don't simply get 75 grams back out the other side. Okay? So first we're going to ask how much of that lead nitrate remains in solution. I know that if I had 100 grams of water, that 37 grams would be remaining in solution, right? That's what my solubility factor tells me. But did I use 100 grams of water? No. So we're going to have to use the amount of water that we actually used in order to calculate here. All right, so we're going to take that 78.947 with our sig fig marked grams of H2O. And we're going to use our new conversion factor here. Do I keep it as is or do I flip it?
No, keep it as is.
I'm going to keep it as is, right? So that my 100 grams of water cancel out. All right, and this is where my whole shtick about like, I don't know if I gave it to you actually. Did I give you the shtick about the scientific calculator? Okay, I would highly recommend. A lot of people try to like use their cell phone and stuff like that. That's like a 4-function calculator, which means that as soon as you do that sort of problem, it instantly gives you the answer. You can't do multi-step problems very easily. The other benefit of a scientific calculator is that I could just go back up and copy that number that I used previously and use that in my future calculation. I don't have to worry about writing stuff down and then potentially not entering it back into the calculator correctly. So just grabbing that number that I used previously or that I got from my previous calculation, multiplying by 37 and dividing by 100. Okay. I get 29.2105 grams of, what are my units here? Grams of what?
Lead nitrate.
Lead nitrate. Okay, but importantly, since we used our solubility factor here, this is telling me the maximum amount of lead nitrate that will stay dissolved in that solution, right? This is still in the solution here. I'm going to mark my sig fig here. So we're just going to note this is how much remains. But now what I really want to know is how much pure lead nitrate has precipitated. Okay, so how the heck am I supposed to figure that out? Cool, right? I know how much I put into that solution initially. How much did I put in initially?
75.
At 75 grams. I know how much is stuck in that solution, how much I'm going to lose when I do my recrystallization. So the difference between those two has to be how much precipitates back out. All right? So when I ask you how much precipitates back out, now we got a math problem, or a subtraction problem on our hands. Okay, we're going to take that 75 grams of lead nitrate. This is how much I had initially. I'm going to subtract with all my sig figs that 29.210 grams of lead nitrate. Let me clean up my units here so it's a little bit easier to see. Okay, the 29.2 again was how much remains. in solution. So the difference between those will be how much pure solid I get back out. All right, now remember we have different rules for subtraction and addition than we do for multiplication division. Our rules for addition and subtraction are all about the position of my sig fig. These two are in the exact same place, but I would have to round to whichever position was further to the left, my least precise measurement here. All right, so in this experiment, I got 45.789 grams of lead nitrate that precipitates. All right, but I need to round to that ones position, so my final answer here is 46 grams of pure lead nitrate. Okay, so again, these are these recrystallization, a purification technique where you dissolve a solid in the minimal amount of hot solvent. We then cool that solution down, and what precipitates out is our pure solid. All right, so what we did first is a calculation to figure out what that minimal amount of hot solvent was that I need. Hot because it was at that high temperature. I cooled it down. I first had to figure out how much remained in that cold solution using the solubility at that new temperature, right? Using our solubility, that's how much remains dissolved. So then the difference between what I started with and what remained in solution, that's how much I get back out that's nice and pure. That's how much precipitates out of that solution. What's up?
Like format-wise, on like quizzes or exams, will it be like one big question, or will it be like how much pure remains in the solution? Does that make sense? Like, will it be two together, or will it be like one big question?
So you can kind of be prepared for all. I'd have to give you some information about the amount of water. If I was going to skip, let's say, to this step here, I'd have to have given you information about how much solid I used and how much water I used in order for you to do that next step.
Okay.
All right?
So it could be either or kind of thing.
Yeah. So, but importantly, you'd have to have like that information about what that minimal amount of solid was, or solvent rather was. Cool. All right, last bit about solubility. We're going to talk about, we talked about solids, specifically ionic solids, and how they dissolve in aqueous solution. And we noted here that they have this temperature factor, right, where they increase in solubility as we increase in temperature. Okay? The last thing that we're going to talk about is Henry's law. All right? Our solubility of the last thing we're going to talk about is solubility of gases. I'm going to note we have this other section on our constants page that we're going to be using for this chapter here, or rather for this section. Okay? So what we're going to talk about next is not solubility of solids. We're going to talk about solubility of gases. Okay? The solubility of a gas depends on two important factors here. The first being a temperature of our solution. All right, and we talked about solubility of solids as a function of temperature. And as we noted, as we increase temperature, our solubility increases as well. Turns out that gases, it's the exact opposite trend, okay? So for our solubility of gases, the effect of temperature, as our temperature increases, a gas's solubility decreases. Right? So the exact opposite of what we saw for our solids. Okay? So why would that be? All right? Importantly, when temperature increases, what's happening at the molecular level? Like if I were to like shrink down in my magic school bus and look at a molecule as temperature increases, what's it doing?
Average velocity.
It's moving around even more, right? Movement is increasing as temperature increases, all right? And what happens is as our temperature increases and our gases in our solution start moving around more, they find each other and they form little bubbles that then just rise up and go away, right? Unlike a solid, our gas can disappear out of that container and be lost into the room, okay? So as temperature increases, I'm going to say our molecular movement increases, molecular motion. This causes our gas particles to find one another and bubble out of solution. Okay? So a common technique that you do in the lab when you really need a nice pure solvent, if you really need pure water, oxygen, for example, naturally dissolves in water. Oxygen's kind of a pain in the butt. It actually interferes with quite a few reactions. So if you need to degas your water, you need to get the oxygen out of it. What do? You heat it up and you stir it. That causes all those little bubbles to bubble out. If you've ever gone to a tap in like an old house and you turn on the hot water and it looks like it's kind of white when it comes out, right? And then you let it sit, all those little bubbles rise to the top. That's just the gas being released from that solution because you've increased the temperature. All right, the other big one, and this is the fancy one that we're going to use our constants page for, is the effect of pressure on a gas's solubility. Okay, as our pressure increases, a gas's solubility, what do we think? Increases or decreases?
Increase.
It's going to increase, all right? And everybody's experienced this. If you've ever had a soda or soda water or something like that, you open up that can and you hear that psh sound, right? Why do you hear that psh sound? Because that can has been pressurized specifically to keep that carbon dioxide nice and dissolved in that solution. When you leave that soda can out on the bench, what ends up happening?
Blow up.
It goes flat, right? Because all the carbon dioxide will eventually leave. Okay? So, as our pressure increases, our gas's solubility also increases. And actually, using that same analogy, I bet you all know the temperature effect as well, right? If we have a cold carbonated beverage, it goes flat way slower than if we have a carbonated beverage on a hot day, right? So again, the effect of temperature on the solubility of that CO2 in our water or in our beverage. Okay. And for pressure, for temperature, we just have this sort of saying about how one increases. If temperature increases, then solubility decreases. Okay, for pressure, we actually have something special. Let's actually just note it on here. We have what's called Henry's Law. All right, Henry's Law is a quantitative relationship between pressure and solubility. It's really not that crazy of a formula, but I put it on our constants page here. This isn't anything you have to have memorized. Okay? This is Henry's law here. So let's just pick this apart. Okay? So S of our gas in our formula, this is the solubility of our gas. For solids, it's pretty convenient to talk about solubility in grams because that's how we measure out solids, right? For gases, you don't really go to the balance and measure them out like that. So instead, our solubility of our gas is going to be measured in units of molar concentration, right? So how many moles per liter we get dissolved in our solution. This factor Kh here is what we call Henry's constant. And that's what our table is here. Okay, so Henry's constant is unique for each gas. Depending on what gas you're talking about, you'll go to go to our constants page here, go to this table, and pull that particular value. Okay, and then P is our partial pressure of our gas in specific pressure units, ATM, atmospheres. Okay, so let's do a sample problem here. Okay, we're going to use kind of a nice real world example here. Air is 21% oxygen at 1 ATM, which is our atmospheric pressure that we're in right now, right? Fresno is real dang close to sea level, so we're sitting at 1 ATM of pressure. Okay, I guess I'm going to be good and put an extra digit on there so we're not limited. 1.0 ATM. What is the solubility of oxygen? So if I had a cup of water sitting out on the table right now in this room of air, which is 21% oxygen, what would be its solubility here? Okay, so my pressure, my partial pressure of O2 would be how many ATM? Cool, yeah, so it's just a simple fraction here. If I'm at 1 ATM and there's 21% oxygen in here, then 21% of 1 ATM is the partial pressure of oxygen in this room. So I'm going to do 21 over 100, right? Whenever we use percentages, we got to convert it back to a fraction by dividing by 100 times that 1.0 ATM, and I would get 0.21 ATM as my partial pressure of oxygen. So then everybody's going to take a second, use this table here, and finally tell me what the solubility of oxygen is according to our Henry's law and pulling that value for our Henry's constant from the table. So since I'm talking about oxygen, I specifically grabbed the value of oxygen from my table, right? My 1.3 times 10 to the negative 3. I'm going to multiply that by that partial pressure of oxygen in the room right now, that 0.21 ATM. All right, my calculator is going to spit out 2.73 times 10 to the negative 4. I'm going to put it in scientific notation since it's a small number. If you want to keep it in standard notation, it doesn't matter. All right, what are my units here? I kind of gave it away when I set up here, but let's just note that it all works out beautifully if we follow our units from our chart. All right, my Henry's constant is in molar per ATM, and my partial pressure is in ATM, so that cancels out to just molar. I'm also going to be good. I have 2 sig figs from my chart and 2 from my pressure. So my final answer here is that my solubility of oxygen is 2.7 times 10 to the negative 4 molar. All right, I'll just note for your homework, you can put your answers in scientific notation as well if you're so inclined. Might not be like super convenient all the time. This wouldn't be too bad. But you would use the E notation, similar to what some of your calculators give. 2.7 capital E, negative 4 with our units molar.
Professor, how long does it take for this to get uploaded up to campus on the study?
So the real limitation is how long it takes for YouTube to process it. But I'll kick it off right now.